Exponential and logarithmic equations, exactly what it sounds like. Equations that are written either in an exponential form or a logarithmic form. There's going to be a variable involved, and we need to solve for that variable. So in this example, we have 256 to the 2x equals 64. Now the way we've learned to do this in the past is to rewrite the exponential equation with a common base. And so what we would get here, 256 is 4 to the 4th. That's raised to the 2x, and 64 is 4 to the 3rd. Using our properties of exponents, this becomes 4 to the 8x equals 4 cubed. And if 4 to the 8x equals 4 cubed, then 8x must equal 3. So then x is 3/8. That's how we've already looked at these types of problems. A new way to look at this type of problem using logarithms, since a logarithm is just a mathematical operation, what we can do is take the log of both sides. I'm going to do log of 256 to the 2x equals log 64. I could use whatever base I want. I'm going to choose to use base 10 simply because the log button on the calculator is base 10, so that makes it easiest. Why the logarithm is helpful is using the power property that we talked about in the last section. This exponent inside the logarithm can be moved out front. So we have 2x log 256. The right side is still just log 64. Log of 256 is just a number. We're trying to isolate the x, so let's divide each side by log 256. I get that 2x is log 64 over log 256, which ends up being 3/4. If you put this in the calculator, you get 3/4. So I have that 2x equals 3/4. Divide each side of that by 2, we get that x is 3/8. Same exact thing we got right over here. So these are just two ways of doing the same problem. The nice part about this way done in yellow is this works 100% of the time when you're trying to solve an exponential equation. This process over here only works if you can rewrite the two sides to have a common base. So if you can, feel free to use this way. But there are going to be problems we're going to look at in the future where you cannot rewrite with a common base and you have to use this method. So this is an example of a type of problem where you cannot rewrite the two sides to have a common base. So we have to use logarithms. Now there are two ways to do that. The method we used on the previous example, where I took log base 10 on both sides and then used the power property, yada yada yada. That's one way. Another way we could use logarithms is to realize that this exponential equation can just straight be rewritten as a logarithm. Log base 6 of 512 equals 4x. Just understanding how to rewrite from exponential to logarithmic form. We've covered how to put something like this in the calculator. You either have the input system on the calculator that makes it very easy and obvious how to plug it in. If you have that, use it. That's fine. I don't care. If you don't have that, then probably you're just going to be using change of base formula. So it's going to be log of 512 over log of 6 equals 4x. So we get 3.4817 equals 4x. Divide each side by 4. We get that x is 0.8704. So, a type of problem that needs logarithms in order to solve it, because you would not be able to rewrite these two sides with a common base. Another example of the same type of thing right here. You can't rewrite this with a common base, I don't believe. No, you cannot. And so again, we're going to be using logarithms. We'll just say log base 5 of 3,500 is 2x. So 5.40, not that, 5.0704 is 2x. Divide each side by 2. We get that x is 2.5352. Easy peasy lemon squeezy. Here, you read through this problem, and what you need to realize, this is an exponential decay problem, meaning we need to use our formula for modeling exponential decay. That looks like this. So we know that P, the principal amount, is 126 million. We know that R is 0.05. T is what they're asking for. We don't know what T is, but we know A of T as well. We have to remember that in this formula, A of T is how much you have at the end. The question is asking how many months will it take you to use 1/4 of the memory. If we've used 1/4 of the memory, then we are left with 3/4 of the memory. And how much did we start with? 3/4 of 126 million. And that is going to give us 94,500,000. And that is our A of T. That's how much there is at the end. And so the question is, how long does it take to get to this point? So we have 94,500,000 equals 126 million times 1 minus 0.05 to the t. Divide each side by 126 million, we get 3/4 equals 0.95 to the t. Rewrite it as a logarithm. Log base 0.95 of 3/4 equals t. Evaluate the logarithm, we get that t is 5.6086, and in this problem t is measured in months. So, a fairly straightforward little word problem. You just have to realize this is the formula you're using. Okay, understanding that P is 126 million, R is 0.05 should be pretty doable. The most difficult thinking aspect here is trying to figure out that A of T should be 94,500,000. How many months will it take you to use 1/4 of the memory? So you have to really think about that and understand they're asking how many months until 3/4 of what you started with is left, and then you have to figure out what 3/4 of what you started with is, 94,500,000. So we've been dealing with exponential equations, now logarithmic equations. Ironically, to solve the exponential equations we were just looking at, we would rewrite them as logarithmic expressions and equations. In this example, the best way to solve this logarithmic equation is actually to rewrite it in exponential form. So log 5x plus 2 equals 2. You have to remember right off the bat that if no base is written here, that it should be base 10. So if we rewrite this in exponential form, it's 10 squared equals 5x plus 2. Subtract 2 from each side, we get 98 is 5x. Divide each side by 5, and we get that x is 19.6. So in these types of problems, once you have it rewritten from logarithmic form to exponential form, the rest of the problem should be just algebra 1 type stuff. Know that 10 squared is 100, subtract 2 over, we get 98, divide by 5, we get 19.6. Check your answers to make sure they work. In this case, 19.6 does in fact work. Same idea here. We want to rewrite it in exponential form to solve it, but we have no idea how to rewrite it in exponential form if there are 2 logarithms present. So instead of dealing with 2, we want to condense that left side into one single logarithm using, in this case, because it's subtraction, we're using the quotient property. So this is log of 2x squared over 5 equals 1. Rewriting in exponential form, 10 to the first is 2x squared over 5. So then the algebra 1, multiply each side by 5, divide each side by 2, and now a little bit of algebra 2 that we have to remember. If x squared is 25, then x could be 5 or negative 5. 5 squared is 25, negative 5 squared is also 25. We've got these two answers. We need to plug them in to make sure they work. And if I plug them in, all I'm doing with x is squaring it. 5 squared is going to be 25 times 2 is 50. Plug all that in your calculator, it works out. If you plug in negative 5, it all works out as well. So our answer is 5 or negative 5. They both work.